mean, variance, and moment derivative function of Poisson distribution. Suppose we have a set of positive random variables, say x1, x2, xn. Then the probability density function of Poisson distribution is given as p of x equals to lambda raised to power x exponential raised to power minus lambda divided by x factorial, whereby our lambda is a parameter, x is a series of random variables. We can say x subscript I, x subscript I. Now here, our x runs from 0, 1, 2, to positive infinity. Now, we want to look for the expected value of this probability density function. Now, the mean. What we want to calculate now is the mean. So, the mean, and the mean is given as e of x equals to summation x from 0 to positive infinity. Then we have x multiplied by the probability density function of Poisson distribution. So from here we're going to have this. Says summation x1 from 0 to positive infinity x. Then this p of x is what we have here. Say lambda raised to power x exponential minus lambda divided by x factorial. So now we can expand this x factorial in order to eliminate this x here. And we expand it once, we're going to have this is equals to summation x runs from 1 now. Can we see that? X runs from 1 to infinity. Then here we have x. We can break this lambda raised to power x down, and we're going to have it as lambda multiplied by lambda raised to power x minus 1. If we follow the law of indices, this is raised to power 1. This one here is going to eliminate this minus 1, therefore remain x. So here we break this down, say lambda multiplied by lambda raised to power x minus 1 exponential raised to power minus lambda. Then we have the whole of this divided by x into bracket x minus 1 factorial. We've expanded this x factorial too. Therefore, this x will cancel this x here. Now, lambda has nothing to do with the random variable here. So we take it as this is equals to lambda summation x goes from 1 to positive infinity. Remain this lambda is power x minus 1 exponential minus lambda divided by x minus 1 factorial. Now, if you look at this here, you notice that this is the probability of all sample space, which is look like exactly like what we have in lambda is power x. Now we're at x1 from 0, 1, 2. Now we have it at x1 from 1 to infinity. So here now we can just say, since we have this now, the x is going to run from 1 to and not other is 0. So now the whole this now is going to be the same. Note summation x1 from 1 to infinity lambda raised to power x minus 1 and summation minus lambda divided by x minus 1 factorial. All this is going to be 1 while we solved the sum of probability of all sample points. The sum of probability of all sample points, and therefore we're going to have this now saying e of x, expected value of x, is going to be lambda multiplied by 1. Instead of the whole days, we have lambda multiplied by 1. Therefore, our E of x will be equals to lambda. So lambda is the mean of Poisson distribution. Alright, now we need to get the variance. And variance of x equals to u of x squared minus e of x all squared. Now this e of x is the mean of the Poisson distribution we've got here. Now we need our e of x squared, expected square value of x. Now we're saying e of x squared will be equals to summation s from 0 to positive infinity, so s squared multiplied by the probability of the probability density function of Poisson distribution, so which is here. Now we said this is equals to summation x from 0 to positive infinity, s squared multiplied by p of x equals to d, so lambda raised to power x, I already say as exponential minus lambda divided by x factorial. Since we are just using x, let's stick to that. Now we're going to have this now, which is going to be x raised to power 2. Now we need to expand this in order to take care of this x raised to power 2. Now here we're saying x raised to power 2 equals to, there is a better way of manipulating this. And how do we do that? We say x into bracket x multiplied by x will give us x squared. Now we say minus 1 plus 1. Minus 1 plus 1 equals to 0. So we are still having x raised to power, x raised to power 2. So therefore we can just take this in this format. So now let's put this down. So we can write this as x into bracket x minus 1 then plus 1. If you have it this way, we're still saying the same thing as x squared. So we are going to manipulate x raised to power 2 into this format. And what do we have here now? So this is equals to summation x from 0 to infinity. Instead of x raised to power 2, then we are going to put this x into bracket x minus 1 plus 1. So x into bracket x minus 1 plus 1, then the density function lambda raised to power x exponential raised to power minus lambda divided by all divided by x factorial So now if you open this bracket here, so we're going to have this equals to summation x from 0 to positive infinity x into x minus 1 multiplied by this, that will give us x into bracket x minus 1 lambda raised to power x exponential minus lambda and divided by x factorial. Then we have plus 1 here, summation x multiplied by 1 multiplied by this, that will be plus summation x from 0 to infinity x lambda raised to power x exponential raised to power minus lambda divided by x factorial. Now if you look at this now, this is exactly what we got when we're looking for the expected value of this Poisson distribution. If you look at this and what we have here, let's say it is the same. Therefore, this is our expected value, the mean of Poisson distribution. So we can rewrite this in this form. So this is equals to, alright, now we can break down this x factorial, and we can also break down lambda raised to power x, and that will give us summation x is, our x is going to run from 1 now? No, our x is going to run from 2 infinity. By the time we expand this in 2 times, we're going to have x into bracket x minus 1. Now we have lambda raised to the power 2 multiplied by lambda raised to the power x minus 2. These two, we cancel these two, we still have our lambda raised to the power x, then exponential raised to the power minus lambda divided by so x into bracket x minus 1 x minus 2 factorial, that is plus the whole this is our expected value of Poisson, which is equals to lambda. So we say this is e of x here. Therefore x cancel x, lambda cancel this. So lambda raised to the power 2 has nothing to do with this formula here. So therefore we take it out. So this is equals to lambda raised to the power 2 summation x1 from 2 to infinity. Then we'll reduce lambda raised to the power x minus 2 exponential raised to the power minus lambda divided by x minus 2 factorial plus our e of x is lambda. So we say lambda. Alright. Say note here. This since x is from 2 and we have lambda x raised to the power minus 2 exponential raised to the power minus lambda here. The whole of this is a typical parameter or the whole sample point of this distribution. And the whole sample point of a distribution is going to be 1. Therefore, so summation x from 2 to infinity lambda raised to the power x minus 2 exponential raised to the power minus lambda divided by x minus 2 factorial will be equals to 1. And therefore, we can have our e of x squared to be equals to lambda raised to the power 2 plus lambda. So now we're now going to look for the variance of this distribution. Like we said the other time, variance of x equals to e of x squared minus e of x all squared. Now our e of x squared equals to lambda squared, lambda raised to the power minus 2 plus lambda minus our e of x, that is the mean of x, which is a lambda. So we have lambda raised to the power 2. This lambda here, we cancel this lambda here. Therefore, our variance of x equals to lambda. So the mean is lambda, the variance is also lambda. Now we need to get the moment generator function. The moment generator function of Poisson distribution. So m subscript x of t equals to summation exponential raised to the power tx multiplied by probability of x, which is a probability mass function of Poisson distribution. This is equals to summation exponential tx multiplied by lambda raised to the power x exponential minus lambda divided by the whatever x factorial. Now we say this is equals to this is raised to the power x, this raised to the power x. We can bring them together and say summation lambda exponential t all raised to the power x exponential minus lambda divided by x factorial divided by x factorial. Now here we're going to use a Taylor series expansion of exponential function. So Taylor series expansion of exponential function. In Taylor series exponential of Taylor series expansion of exponential function is in summation lambda exponential t raised to power x divided by x factorial will be equals to exponential raised to power lambda exponential raised to power t. So if the whole is here, which is this what we have here, equals to exponential lambda exponential t, therefore our moment derivative function will become exponential lambda exponential t multiplied by exponential raised to power minus lambda. So exponential raised to power minus lambda. So our moment derivative function x of t now will be equals to exponential is come out say exponential and we have lambda, say lambda into bracket exponential t minus 1. So this is the moment derivative function of a Poisson distribution. Now we can derive the mean and variance from this moment derivative function. So mean of Poisson distribution from moment generating function. That is what we're going to do now. We're going to use another way around to get the mean and variance that we've already gotten earlier here, which is a lambda, and the variance too is also lambda. Now I want to use a mean, I want to use moment generating function. So let's go. So the mean equals to a of x equals to m prime of x when t equals to 0. So first of all, we need to differentiate this. Mx of t equals to exponential lambda into bracket exponential t minus 1. Now, m prime x of t, the derivative of this a moment generated function. We will find the derivative of this moment generated function. So this way we're going to have we are differentiating with respect to t. If you differentiate this with respect to t, therefore we're going to have lambda exponential t. If you differentiate this, we're still going to have lambda exponential t. Then we're going to have this. This is just like a function of a function. It is a lambda exponential t multiplied by lambda raised to power exponential raised to power lambda into bracket exponential raised to power t minus 1. This is the first derivative of this moment generated function. Now for us to get on the mean, which is a of x, so we have to let our t to be equals to 0. That is when t equals to 0, we have lambda exponential 0 multiplied by lambda exponential raised to power lambda into bracket exponential 0 minus 1. So here we're going to have a lambda multiplied by exponential raised to power 0, that is 1. So here now we're going to have this is already 1, so we have an exponential lambda into bracket 1 minus 1. And this will give us lambda exponential raised to power lambda is 0. And since this is equal to 0, lambda times 0 is 0. Exponential raised to power lambda, the whole of this is going to give us 1. Therefore, mx of t, which is equals to e of x, will be equals to lambda, because this is the whole this will be equals to 1. The whole is equals to 1. The lambda is lambda multiplied by 1 give us lambda. So the variance here of cells. Like we said the other time, variance of x equals to e of x squared minus e of x all squared. This is equivalent to say m prime prime x when t equals to 0. That is the second derivative. And when t equals to 0 minus m prime x when t equals to 0, then we'll say square. So that will give us the variance of this distribution. So we need to find the second derivative of the distribution here. So the first derivative is here. We are still differentiating this further. Then m prime prime subscript x of t, m prime prime subscript x of t, that is, we are going to differentiate this and keep this. If we differentiate lambda exponential t, we're still going to have a lambda exponential t, the one we keep here, exponential lambda, into bracket exponential t minus 1, then plus. Now we're going to keep this and differentiate this. If we keep this and differentiate this, we're going to have a lambda exponential t multiplied by lambda exponential t exponential lambda into brackets exponential t minus 1. This is the second derivative of this of the first derivative here. And when t equals to 0, we have m prime prime x of 0 equals to lambda exponential 0 exponential lambda into bracket exponential 0 minus 1 plus lambda exponential 0 multiplied by lambda exponential 0 exponential lambda exponential 0 minus 1. And here we're going to have lambda, the whole of this here value here, since we're going to have exponential 0 here, will give us 1. 1 minus 1 is 0. 0 multiplied by lambda is 0. Anything raised by 0 is 1. So this is raised multiplied by 1. Then plus, we have lambda. Same thing is still going to happen here. So this is lambda, then multiply by lambda. So the whole that's this here is going to be 1. So therefore, because we're going to have 1 minus 1 by 0. So this is equals to lambda plus lambda multiplied by lambda. That is the lambda raised to power 2. So our m prime prime s of 0 equals to lambda plus lambda raised to power 2. And we should not forget our m prime equals to lambda. So now the variance is now equals to, says lambda plus lambda raised to power 2 minus lambda raised to power 2 from this formula here. Like we said the other time, m prime prime of 0 minus m prime 0 raised to power 2. And our m prime of 0 here, m prime x of 0 equals to lambda. So here we have lambda plus lambda square minus lambda square. Lambda square will cancel lambda square. Therefore, the variance of x equals to lambda. So the mean is lambda and the variance is also lambda.